There's an object in our galaxy so magnetic that if drifted halfway between the Earth and the Moon, it would wipe every credit card and erase every hard drive on the planet. Get within 1,000 kilometers of it, and its field will pull your body apart, atom by atom. It's called a magnetar, the most magnetic object in the known universe. And for the first time in history, astronomers have just watched one being born. To understand a magnetar, you have to know what it's made of. When a massive star runs out of fuel, its core collapses, and the blast that follows is a supernova. What's left behind is one of the strangest objects in physics, a neutron star. Take the entire mass of our Sun and crush it into a ball about 20 kilometers across. That's the size of a city. The matter is so dense that a single teaspoon of it would weigh billions of tons. Most neutron stars are extreme enough on their own. They spin fast, some of them hundreds of times per second. But a small fraction are born with something far more violent. As the core collapses, under the right conditions, a kind of dynamo switches on inside it, winding the magnetic field tighter and tighter until it locks in a strength nothing else in the universe can touch. That's a magnetar. Earth has a magnetic field. It's what nudges a compass needle north. A magnetar's field is somewhere around 1 trillion times stronger. By an enormous margin, it's the most powerful magnetic force we know of anywhere in existence. At that strength, magnetism stops being something subtle and starts rewriting matter itself. The field is so intense it physically squeezes atoms out of shape, stretching them from round into thin needles lined up along the field until ordinary chemistry simply can't function. That's why astronomers like to point out what would happen if a magnetar passed within 1,000 kilometers of you. You wouldn't be crushed or burned. The field would strip the electrons of every atom in your body, leaving a cloud of bare nuclei. You would stop being matter as we understand it. And that's a magnetar just sitting there, quiet. When one of them loses its temper, it does something that can reach across the galaxy and touch us directly. A magnetar's field is so strong, it puts the solid crust of the star under unbearable strain. Every so often, that crust cracks, a starquake. When it does, the magnetic field snaps and violently reconnects, releasing a burst of energy called a giant flare. On the 27th of December 2004, a magnetar called SGR 1806-20 let one of these flares go. In a fraction of a second, it released more energy than our Sun puts out in 250,000 years. That magnetar sits roughly 50,000 light years away, halfway across the galaxy. And when the flare reached us, it physically disturbed the upper atmosphere of the Earth, ionizing part of it and leaving a measurable mark on our planet's magnetic field. A star, half a galaxy away, reached across that distance and changed conditions in our sky. Nothing else we know of can do that from so far. For decades, magnetars were almost a theory you had to take on faith. We could see their flares. We had never actually caught one being made. Until now. In December 2024, astronomers spotted a supernova about 1 billion light years away, catalogued as SN 2024 AFAV. It was a superluminous supernova, at least 10 times brighter than a normal one, and far too bright for an ordinary explosion to explain. A global network of telescopes called Las Cumbres Observatory tracked it for more than 200 days. Most supernovae fade smoothly. This one didn't. As it dimmed, its light flickered, 4 distinct bumps in brightness, and each gap between them was shorter than the one before, a speeding up pulse, a chirp. More than a year later, in 2026, a team led by Joseph Farah finally worked out what was producing it. At the center of the explosion sat a newborn magnetar, spinning every few milliseconds. Debris from the blast was falling back and forming a disk around it. But the disk was tilted, misaligned with the magnetar's spin. The magnetar was spinning so fast and was so dense that it was dragging the fabric of space-time around it, making the tilted disk wobble like a spinning top. As the disk spiraled inward, it wobbled faster, producing that accelerating chirp in the light. To describe that wobble, the team had to reach for Einstein's general relativity. It was the first time in history that general relativity was needed to explain the mechanics of a supernova. The chirp was the signature of a magnetar being born, and it confirmed the 16-year-old prediction by astrophysicist Dan Kasen that these objects are the hidden engines behind the brightest explosions in the universe. So, we finally caught one in the act, and almost at the same moment, magnetars were caught doing something else nobody expected. This discovery ties two extremes together. The most magnetic objects in the universe turn out to be the engines behind some of its brightest explosions. A newborn magnetar, spinning hundreds of times a second, dumps its energy into the surrounding debris and lights it up far beyond what the blast alone ever could. For more than 20 years, these superluminous supernovae had been a puzzle. They shone too brightly, and stayed bright for far too long for any ordinary explosion to account for. The magnetar idea was the favorite answer, but for 2 decades it was just that, an idea no one had ever confirmed by watching it happen. SN2024 AFAV is the confirmation. They've also been tied to one of astronomy's strangest signals, fast radio bursts. Millisecond blasts of radio energy from deep space that puzzled astronomers for years. They were partly solved in 2020 when a magnetar inside our own galaxy was caught firing one off. At least some of those mysterious signals are magnetars flaring. It was the first time one of those bursts had ever been traced to a source inside our own galaxy. And magnetars are fleeting. The monstrous field decays. Within about 10,000 years, the activity dies down and the magnetar goes quiet. On a cosmic timescale, that's the blink of an eye. The Milky Way is thought to hold tens of millions of these burnt-out, silent magnetars drifting in the dark, their fields long gone. The active ones we can actually catch flaring are rare. Only a few dozen are known. And the central question is still wide open. How does a neutron star build a field that strong in the first place? Why do a small fraction of them become magnetars, while the rest settle down into ordinary pulsars? We have the dynamo idea, the furious churning in the first few seconds of the star's life, but we still can't predict which stars do it, or exactly how the field gets locked in. As Farah put it, a discovery like this is the universe telling us, out loud, that we don't fully understand it yet. What we do have now, for the first time, is a way to watch it happen. The chirp is a brand new tool. With bigger surveys coming online, astronomers expect to find dozens more of these chirping supernovae, and each one is a magnetar being born in real time that we can finally study from the very first moments. A magnetar is what's left when a dying star collapses into something so extreme and bends the rules of matter, cracks under its own magnetism, and reaches across the galaxy to disturb our sky. For half a century, it was almost a rumor, an object too strange to observe directly. Now, we've watched one take its first breath in the light of an explosion a billion years old. If this one was worth your time, a like genuinely helps the channel grow. This channel is about exactly these moments, when something we thought we understood turns out to be stranger. Subscribe if that's your kind of thing. Thanks for watching. Clear skies.